Unit 1A, Lesson 6. This lesson will align with 12.2 in your textbooks. One standard we are going to discuss in this lesson: use the structure of an expression to identify ways to rewrite it. Okay, for example, if we have x to the fourth minus y to the fourth, we can rewrite that to use the difference of squares patterns to factor it out. To start off this lesson, we're going to go through some exponent properties we talked about in Algebra 1. The first one is the product of powers. We have a base that is the same. Base is x, we're multiplying. So if that's the case, we add our exponents. This will become x to the 13th power. Next, we have the power to a power. If we have an exponent raised to another exponent, we need to multiply. So this will be x to the 42nd power. Next one is the negative exponent property. We always want to write our exponents positive when we're in simplified form. So to do that, we have to use a reciprocal property. This will become 1 over y to the third power. Next one, we have a set of parentheses. We have two factors being multiplied inside, raised to a power. We have to distribute this power to each of those factors. This will become 2 cubed times x cubed, which we can simplify to 8x cubed. Next one, very similar, except we have a quotient. We have to distribute this power to the numerator and the denominator, which will give us x squared over 2 squared, which will simplify to x squared over 4. And the last one is our zero exponent property. Anything raised to the 0 power is 1. These are all properties we've talked about previously. Go through, refresh your memory on them. Make sure you understand these because we will use these in the upcoming lesson. Getting back to more of a focus on our standard for this lesson, we have x to the fourth minus 16. We want to rewrite this expression using factoring ideas we've talked about previously. First thing, we can rewrite each of these terms. I know x to the fourth is the same as x squared raised to the second power. So our power to a power property we just discussed. I also know 16 is the same as 4 squared. I have some quantity that is squared minus another quantity that is squared. This is our difference of squares property. We know how to use the difference of squares property. This will factor into x squared minus 4 times x squared plus 4. Again, we have a difference of squares, which we can simplify. This will factor into x plus 2 times x minus 2. X squared plus 4, that is not going to factor nicely, but we have talked about this previously when referring to complex numbers. If we have a sum of two squares, we know there's going to be some imaginary numbers involved. This will factor into x plus 2y times x minus 2y. Normally, we're not going to factor this down any further, but it's good practice for what we've talked about previously with complex numbers. Using the ideas of difference of squares, first we had to use exponent properties to rewrite this expression, then we could apply the difference of squares to factor it down. Another example, very similar. If you would like to pause the video, this would be a good chance for you to practice rewriting this using exponent properties and then difference of squares. Okay? If you're not comfortable yet, you can watch me go through it right now. So 4x to the fourth, I want to use exponent properties to rewrite that. Have to be a little creative because this time we have a coefficient other than 1, but 4 is a perfect square. So this is going to be some expression raised to the second power. I know 4 is the same as 2 to the second power, and x squared is the same as or x squared to the second power is the same as x to the fourth. Y to the fourth, we can rewrite that as y squared to the second power. So very similar to the last problem. The only difference is because we had a coefficient other than 1, we had to count for that factoring that product inside the parentheses raised to the power. Now we can go through and use the difference of squares. We have 2x squared minus y squared times 2x squared plus y squared. Using exponent properties again, rewriting that, and then using difference of squares to factor that out. It is perfectly fine for us to stop at this point. Okay, we have a sum over here. We know we can't break that down nicely. And over here we have that difference, but 2 is not a perfect square. Okay, so if we try to factor that out using a difference of squares, it's not going to end up nicely with rational coefficients. Technically, we can apply the difference of squares to break this down though. And I'm going to show you right now how we could do that. 2 is the same as radical 2 squared. So if I wanted to break this down further, I'm just looking at this first expression right now, 2x squared minus y squared. I'm going to apply a difference of squares property to factor this down further. This would be the same as radical 2x minus y times radical 2x plus y. And then we still have the 2x squared plus y squared at the end. So even though we have a number 2 that is not a perfect square, technically we can still break that down using the same ideas we did when we had the coefficient of 4. So this is our final factorization. Normally, if you have a standardized test, you will only have to go to this step because 2 is not a perfect square. To end this lesson, we're going to talk about Pascal's triangle and the binomial theorem. We're not going to go real in depth with this. I just want to give you an introduction because we're going to work more in depth with these in the next unit. Okay, so Pascal's triangle, this has applications that allows us to understand and know the coefficients when we try to expand a binomial. If we look, this is called row 0. This is actually row 1, and this is row 2. Okay, and we can go down the list. We got 3, 4, 5, 6. We always start each row and end each row with a 1. How we come up with all these numbers in the middle, if I add the two numbers above, 1 plus 1 gives me 2. 2 plus 1 gives me 3. 3 plus 3 gives me 6. 6 plus 4 gives me 10, and so on and so on. All right, so look through, recognize Pascal's triangle, be familiar with it. We're not going to go real in depth right now. I just want to give you some background so it's not completely new when we go into it later on. This is going to look even more confusing than Pascal's triangle. This is the binomial theorem. We will work with combinations, that's a statistics idea, when dealing with the binomial theorem. Okay, so this binomial theorem says that we can expand using this summation notation. All right, NCR, that's standing for a combination, A and B standing for our variables. These values, NC0, NC1, NC2, those are going to be same values that we can find in Pascal's triangle. All right, so right now, I know this is really confusing. You should just write this down in your notes. I just want to introduce you to Pascal's triangle and the binomial theorem. That way you've heard them before, seen what this foreign language looks like. That way it's not completely new when we discuss it later. The main thing you need to gain from this lesson is understanding all of those exponent properties we went through in the beginning and applying those so that we are able to rewrite an expression to apply properties like the difference of squares in order to factor out more complicated expressions.